Aside from the covalent bonds that we have talked about in the previous video, the atoms of elements may also bond together with a non-covalent bond. So in this particular presentation, we are going to go through the 4 types of non-covalent bonds. So firstly, there is the bond that is created due to the transfer of electron from one atom, in this case sodium, to another atom, in this case chlorine. So this transfer of electron accomplishes the same point as the sharing of electrons. So because of the transfer of electron from sodium to chlorine, sodium will now have 8 valence electrons and chlorine will also have 8 valence electrons. Thus, both of their atoms will be gaining stability. But as a consequence of the transfer of the electron, which is a negatively charged particle, the chlorine atom gains a negative charge and is now called the chloride ion, while the sodium atom gains a positive charge and is now called the sodium ion. So the opposing charges of these two ions causes them to attract each other, and that attraction is what we call as the ionic bond. So the ionic bond is the first type of non-covalent bond. So many substances are actually ionic in nature because their particles are bonded together ionically. So a very good example is your table salt or sodium chloride. So it's crystalline in structure. You can see here the different ions comprising a crystal of table salt, blue for the chloride anion, and gray for the sodium cation. And when we put a crystal of salt in water, and we've learned that water molecules are actually partly charged, they are polar, the water molecules are going to aggregate around the sodium cation with the oxygen pole of the water molecules facing the sodium cation. And other water molecules will also be aggregating around the chloride anion, but this time around, the positively charged hydrogen pole of the water molecule will be the one facing the chloride anion. So this action of water towards salt is the reason why water can dissolve salt easily and readily. So in this case, salt has dissociated from sodium chloride. It has become sodium cation and chloride anion in water. So you now have a salt solution. Then water molecules by themselves also attract each other. So you can already imagine each water molecule has a partly or partially negative pole and a partially positive pole. So when placed together, these water molecules are going to orient themselves such that the partly negative pole of one water molecule will be attracted to the partly positive pole of another water molecule. So this is the structure of the water, showing the water molecules when it's in liquid state. And when we freeze water, these water molecules are actually going to arrange themselves in a lattice, in a crystalline structure. As a consequence, there are bigger air spaces in between the water molecules, and we have ice. So this is the reason why ice floats on liquid water, because it's actually less dense because of these air packets between the water molecules in ice. So this particular bond between water molecules between its hydrogen atoms and oxygen atoms is called the hydrogen bond. So this is our second type of non-covalent bond. And this is just evident when you see in this particular experiment that water would actually stick with each other and they will avoid spilling, and that's because of the very strong hydrogen bond between the water molecules. Well, don't get me wrong, one hydrogen bond is very easy to break, but if there are millions of them, they are going to be really, really strong. So hydrogen bonds may also happen between the hydrogen portions of other molecules and the electronegative atoms of other molecules. So you can see hydrogen bonds here between hydrogen in one molecule and oxygen and nitrogen in another molecule, especially when these molecules are polar, like water. Then here we see an illustration of two blobs, gray blobs. These gray blobs are actually hydrophobic substances, substances that hate water, like droplets of oil. What happens when you put a droplet of oil in water? The tendency is they will stick together. The droplets would tend to stick together to form a bigger droplet, thus separating themselves from water. So there is sort of a bonding between the hydrophobic entities that we see here in gray, but it's not really because they are attracted to each other. The reason why they have stuck to each other is because the water molecule surrounding them is trying to push them together. And this bonding, quote unquote, of these two hydrophobic molecules results in a lesser surface area exposed to the water. And so this is a favorable configuration for the two hydrophobic droplets. So here we have hydrophobic interactions, the third type of non-covalent bonding. But they are not really true bonds because it's not the hydrophobic particles attracting each other that's causing them to bond, but instead it's the molecules surrounding them that's causing them to come together. Imagine two people who do not like each other and they are in a crowd of people. But then the crowd of people try to push them near each other even though they don't like each other. And so they are forced to stick together just to avoid unnecessary pushing. And then they sort of quote-unquote bond together even though it's not really a true bond. Then here we have two atoms. When they are far apart from each other, atoms which have a positive center and a negative periphery, they don't interact if they're far away from each other. Okay? So we're talking here about really, really small distances measured in angstroms. Okay? That's the unit of distance that we are going to use in atomic level. But when these atoms are held together closely, too close in fact, they would start to repel each other. So their negative charges, their electrons will repel each other, as we can see here. But if they are placed near each other at just an enough amount of distance in angstroms, they would also attract each other's electron cloud. So the story here is if two atoms are far apart, then there's no interaction. If they're too close, they will repel. But if the distance between them is just right, then they will attract each other. So this is what we call as van der Waals force. So we can see in this particular graph that if you put two atoms really closely together, they will repel. And if you put them at just the right distance, they will attract. And if you put them farther away from each other, there will be no interaction between them at all. And this van der Waals force is actually at work every time when an antibody sticks to an antigen. I hope you can recall your antibody-antigen interaction. They do stick together because their atoms are just at the right distance, as shown in this particular illustration. So, van der Waals forces are the fourth type of bonds that are non-covalent. And van der Waals forces are also used by certain animals like lizards to stick onto surfaces even if they're upside down, because their feet actually have microscopic thin hair-like structures that can stick really closely to the surface of the ceiling, so that the atoms between their feet and the ceiling are just enough in distance so that they attract each other. Again, van der Waals force.